Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class, we'll discuss about the microstrip antenna. Microstrip antenna is one of the very popular antenna nowadays, and variants of microstrip antennas are used in mobile phones and satellite communications, and all kinds of application has microstrip antenna as one of the components nowadays, and it's very popular because of this planar structure. So but question is, how does a microstrip antenna look like? So the three main components of a microstrip antenna is the pads. So this is a pads here. This base is in rectangular shape. This is the top view. If you look at the microstrip antenna from the side view, pads is here. It can be of any shape, rectangular, circular, different shapes you can have. And what do you do? Basically, this patch is printed on a dielectric substrate. This is the substrate. So the first part of the microstrip antenna is the patch. The second part is the substrate on which this patch has been printed. Then in the lower part you have a ground plane, which is also completely metal. This patch is metal metal. This ground plane is also metal metal. So if you want to fit this patch, basically microstrip antenna or any kind of antenna is a passive device. You need a source to excite this antenna. So usually we use coaxial cable. Coaxial cable will have inner conductor and outer conductor. This is the outer conductor, this is inner conductor. How do you fit this microstrip antenna or pads? Is basically you connect the outer conductor of the coaxial cable to the ground plane and inner conductor to the pads. That's how you do the coaxial cable feeding of the microstrip antenna. So in the microstrip antenna, the main component is the pads. Then you have a dielectric substrate. Then you have a ground plane. So these are the three components of the microstrip antenna. And these pads can be of various shapes. It could be rectangular, circular, square, triangular, semicircular, sectoral, annular, ring. You can have different kinds of shapes according to your requirements, according to your application specification of the antenna. In this class, we'll discuss about the simple patch, which is rectangular in shape. This patch here is rectangular in shape, right? Just before this, we have discussed about the coaxial fit. We can also have microstrip line fit to this patch antenna. So we connect a microstrip fit line. The source is here. Then you connect it to the microstrip fit line. Then this will excite the patch and it will start radiating. So this is the dimension of the patch. You have a length and width here. And sometimes you fit this microstrip fit line at a location at a distance x1 from the edge, so that at this edge the impedance matching is not proper. You need to displace it little bit, cut a slot here, small slot here, and fit the patch at a slightly at a slight distance of x1 from the edge of the patch, so that you can have a proper impedance matching. Let's say this fit line is having a characteristic impedance of 50 ohm, then looking at this point, this patch should also have an input impedance of 50 ohm. Then only will not have any reflection. So all the signals which come from the source through the microstrip line will go to the patch antenna. Then patch antenna will radiate the signals. How does radiation occurs from the microstrip antenna? So basically this is a fit line. So basically, when does a radiation occur? Radiation occurs when there is acceleration or deceleration of charge. So acceleration or deceleration of charge is maximum when you have a discontinuity. For example, you have a microstrip line here. It has been continuous. Had it been continuous, then signal will be flowing in the microstrip line. There won't be much radiation. But here, what do you see? This microstrip line here, this microstrip line has a transition from this microstrip line to the patch. So because of this transition from the microstrip line to the patch, there will be some acceleration or deceleration of charge. Because of that, we'll have radiation from this slot here. Again, this signal which has gone here, it will reach this open circuit. This open circuited is terminated. No, this metal has been terminated here. This open circuited signal will be reflected back. So here, when this signal which has come from the microstrip line through the page, when it sees a termination, there will be deceleration of charge here. So because of that, there will be a lot of radiation. So whenever you have acceleration or deceleration of charge, there will be a lot of radiation. So for that to happen, you should have a termination, or you should have a change in the size of the transmission line from the transmission line to that of the page. So assume a signal which is incoming from the microstrip line. What does this signal which is propagating through the microstrip line sees is a patch. This patch actually is metal, and you also have a ground plane below, and actually it can be assumed as a parallel plate transmission line. You have a metal plate in the patch. Patch is a metal plate. You also have a metal plate in the ground plane. In between you have a dielectric substrate. So you can assume a simple model for this patch is it's a low impedance parallel plate transmission line. And you can even find out the characteristic impedance from for a parallel plate transmission line. For parallel plate transmission line, the characteristic impedance is ZOP. P for parallel plate is approximately eta naught. Eta naught is free space wave impedance or intrinsic impedance divided by square root of epsilon r. Height of this, and W is the width. This width is W. What is height? Height is this. Height of the substrate. So once we have the height of the substrate, we know the width of the patch, we can find out the characteristic impedance of the equivalent low impedance parallel plate transmission line as eta naught by square root of epsilon r S by W. So as I've already told you, signal which has come from the microstrip line will see some kind of changes in the dimension of the width of the microstrip line from the microstrip line. Let's call it WM here to W. There is a discontinuity here. Again, you have a termination here. Because of that, there will be radiation at this layer and this layer. We call this as slot 1 and slot 2. So at this point you have a slot, you also have a slot here. These two slots will be radiating. And you can observe that these two slots has a distance of L. So basically there's one slot here, this is slot 1, this is slot 2. So this slot 1 will also be radiating, slot 2 will also be radiating. So this is slot 1 and slot 2 can be assumed as a slot antenna 1, slot antenna 2, and you can apply array, antenna element array. This looks like a 2-element slot antenna array. You can find out the radiation pattern easily. We are actually interested in the aperture model of the microstrip antenna. So we have one aperture here, slot 1, another aperture here, slot 2, and this antenna array, you apply the antenna array principle, you find the radiation pattern of this two slot aperture array. Just before that, we need to know what is the field here, how is the field distribution here in slot 1 and slot 2. First thing is that the height of the microstrip antenna, this height of this substrate H is usually very small with respect to lambda. H is of the order of 0.1 lambda. So in that case, you can assume that fields are uniform in that slot, and you can write it as, we have a, basically this is a diagram here. You have a slot here. We are considering the slot at Z is equal to L by 2. We'll have another slot at Z is equal to plus L by 2. So the distance between the two slots would be L. So let us try to find the fields, far field radiated patterns of the microstrip antenna. So the usual step is first stabilize the fields and aperture, then you find the 2D Fourier transform and find the fields using equation 24.1 and 24.2. Usual step for any kind of aperture antennas, and the microstrip antenna is also considered as can be considered as an aperture antenna. So let us try to find the fields in the aperture in the slot. So this slot has a height of h. This is x is equal to 0, this is x equal to h. So now you have, since the height is very small with respect to lambda, we have a uniform electric field here across the slots. This is a ground plane, This is a microstrip plane. This is a ground plane, this is a microstrip plane, and the width of the microstrip antenna is W. This is y is equal to minus W by 2. This y is equal to W plus W by 2. This location is at Z is equal to minus L by 2. This is the x-axis, this is z axis, this is the y-axis. This z is equal to minus L by 2, this y is equal to minus W by 2, and this y is equal to plus W by 2, and this is x is equal to 0, this is x is equal to h. We have electric field, uniform electric field, which is going from x is equal to 0 to x is equal to h, from the ground plane to the microstrip plane. What does this look like? This looks like a vertical electric dipole. We have a ground plane here. Ground plane is a, you can assume ground plane is infinite, but we have a finite ground plane. So above the ground plane we have a vertical electric dipole. So this looks like vertical electric dipole above the ground plane. We have a ground plane here. So above that we have this vertical electric dipoles. So whenever we have a ground plane which is made of metal, perfect electric conductor, I can apply the method of images and remove the ground plane, so that I can find out the fields in the region above the for value of x greater than 0. So if we apply the principle of method of images, then what do I have? So this was the original vertical electric dipole. Let us just consider one of them. So now there was a ground plane here. We remove the ground plane, and there was a ground plane here at this plane. In order to satisfy the boundary condition of the original problem, I need to introduce a image current density, and from your method of image you know that the direction of this image current density should be also along the same direction, because this is like a vertical electric dipole. Vertical electric dipole over a infinite PEC surface, its image will be also directed along the same direction. So in this figure what we have done is we have extended this slot. We have considered in the previous case this slot was having a height of just h, but here because of this image also along the same direction and same amplitude, we can have a slot whose height is from x is equal to minus h to plus h. So this is a model of slot aperture field using method of images. We have a electric field, uniform electric field from x is equal to minus h to plus h, y going from minus y by 2 to plus minus w by 2 to plus w by 2. And what is this location of this slot? Number 1, it has z is equal to minus l by 2. We'll have another slot at z is equal to plus l by 2. So the updated aperture field will be x hat E naught from minus h. Previously it was from 0 to h, but now it will be minus h to plus h. Y going from minus w by 2 to plus w by 2. Elsewhere is 0. That's not all. We can still apply the principle of images. See, basically what we have assumed is electric field is assumed to be 0 everywhere. See, aperture electric field is 0 elsewhere. It is having a uniform field directed along the x-axis within this aperture only. So outside this everything is 0. So in that case we can even assume this outside this slot portion as an infinite perfect electric conductor. You can do that because you know that there is a very small field exists in the region z less than 0, z less than minus l by 2. This should be z less than minus l by 2. Then we can assume that there is a perfect electric conductor here at z is equal to minus l by 2. You understand the argument? Argument is that since the electric field is assumed to be 0 everywhere except over the slot, it looks like a uniformly excited aperture in an infinite ground plane. So you can assume that there is an infinite ground plane here, there is a uniform excited aperture here. So in that case I can still apply method of images here. So I can find out the equivalent source over the slot. It would be minus z hat cross product with EA. We have the value of EA, x hat, E naught. This is over the slot. So I can find out the equivalent magnetic current density here and replace the slot by equivalent magnetic current density. And look at this. This looks like this direction is along the minus y direction and it is having amplitude of E naught. This is the original one. But now this looks like a horizontal magnetic dipole because we have an infinite horizontal magnetic dipole because we have an infinite PC surface here. So if I replace that PC surface, this was an infinite PC surface you have here, assume here, and if I remove that PC surface and apply the method of images, so in order to satisfy the boundary condition of the original problem, I should have an image, and this looks like a horizontal magnetic dipole. A horizontal magnetic dipole image will be along the same direction, and they are actually located at the same location. I have shown it slightly displaced for easier visualization. So they are at the same place, same direction, same amplitude. So in that case, after application of method of images, this magnetic current density will be twice. So the magnetic current density will become minus y hat 2 E naught. So we have a factor of 2 because of application of method of images. So equivalently, we can multiply a factor of 2 in the aperture field. So the aperture field will have, so we can write the aperture field after application of the method of images as EA is equal to 2x hat E naught from minus h to h minus w by 2 plus w by 2. Everywhere else is 0. So you will have a 2 factor here. So if you want to find the far field radiation pattern of this microstrip antenna, I need to know what is the 2D Fourier transform of this aperture field. What is the aperture field? It's 2 E naught from minus h to plus h minus w by 2 to plus w by 2. You integrate it after multiplying with exponential j beta x x dash plus exponential after multiplying with exponential j beta x x dash plus j beta y y dash integrated over dx dash and dy dash. This is the definition of 2D Fourier transform, and this integration usually is from minus infinity to plus infinity, but our electric field over the existing was existing only over the aperture, and aperture is area is from minus h to plus h minus w by 2 plus w by 2. All outside this there is no field. So you can find out this integration. You have already done similar kind of integration. It will give us sinc function. So finally the integration would be 4 E naught h w sinc of beta x h sinc of beta y w by 2. This is very simple integration. So we have the 2D Fourier transform of the aperture fields. Once we have that, we can find out the far field radiation pattern using the equation 24.1 and 24.2. This is the expression for equation 24.1 and 24.2. But in this case, we only have x component of the electric field. So only this term will be non-zero. Only this term will be non-zero. All other terms will be 0. So electric field in the far field of this microstrip antenna will have theta and phi component like this. So you can plug in the 2D Fourier transform. See here tilde means is a 2D Fourier transforms. It's also 2D Fourier transform of the x component of the electric field. So they are all sinc function, two sinc functions. So you can find out electric field and far field of the microstrip antenna. Theta component is this, phi component is this. Yes, I have already told you the height of the substrate is usually of the order of 0.1 lambda. So in that case, h is very much lesser than lambda. If h is very much lesser than lambda, what happens to this beta x h? Beta x is beta h sin theta cos phi. When h by lambda is a very small number, this tends to 0. So sinc of 0 is 1. So this term will go away, this term will go away. So the electric field in the far field theta component will have this expression, and this sinc function, this sinc function will become 1. So this is a simplified expression for microstrip antenna in the far field theta and phi component electric field. So whatever calculation we have done is for a single slot. As I already told you, will have two slot, one at z is equal to L by 2, another is at z is equal to L by 2. The distance between the two slot is L. This is slot 1, this is slot 2. So this is a two slot antenna array. So I have already found out the far field radiation pattern of a single slot. If I want to find the radiation pattern of the microstrip antenna, I need to apply array principle, pattern multiplication principle of antenna array, find out the array factor for this two slot and multiply with that of the electric field in the far field of a single slot. So let us try to find the array factor. Array factor is, you can simply find out, array factor is exponential j beta dot r dash r1 dash plus exponential j beta dot r2 dash. You know what is r1 dash and r2 dash. R1 dash and r2 dash are the location of the slot 1 and slot 2. So the location of slot 1 is r1 dash is minus L by 2 z hat. So this is located at z is equal to minus L by 2. This is located at z is equal to L by 2. R2 dash will be L by 2 z hat. So the array factor will simply become exponential minus j beta z L by 2 plus exponential j beta z L by 2. So this you can express in terms of cosine function 2 cos of beta z L by 2. What is beta z? Beta z is beta cos theta. So the final expression for array factor is 2 cosine of beta z or beta cos theta L by 2. So you multiply this with the electric field in the far field theta and phi component of the single slot with the array factor, then what you have is the radiation pattern in the far field of a microstrip antenna. Note that beta y is beta sin theta sin phi. That's a projection of beta vector along the y-axis. So we have the radiation pattern of microstrip antenna. Once we have the radiation pattern, what do? We plot it in the E plane and S plane. In the E plane, phi is equal to 0. YZ plane, phi is equal to 0 means YZ plane. When you put phi is equal to 0, this will become 1, this will become 0. So we'll have only theta component of the field. E theta component will be 2j beta exponential minus j beta r divided by pi r. E naught is omega cos of beta L by 2 cos theta. S plane would be when theta is equal to plus minus pi by 2. So when theta is equal to plus minus pi by 2, S plane will be there. So for the S plane, it will also have only theta component of the field, phi component will become 0. This is the expression for the S plane of the microstrip antenna. And the typical values of dimension of the microstrip antenna is L is lambda g by 2. Lambda g is basically lambda by 2 square root of epsilon r. W is lambda by 4. These are the typical values. S is 0.1 lambda and epsilon r is 4.4 for the PCB board, FR board, which is the most widely used material for fabrication of microstrip antenna at the low frequency. If you go for high frequency, you need to go for a low loss material like RT dioxide substrate. FR4 is usually for you work it for 1 to 10 gears. If you go for higher frequency, you have to go for RT dioxide substrate because the loss tangent for RT dioxide substrate is very low. Loss tangent for FR4 board is very high, but you can use it for low frequency applications. See, once you put in this dimension values in this expression, you can easily plot this radiation pattern in the E plane and S plane. And since I don't have much time to do that, you can always do it. This is a very simple expression you have here. One is cosine function and is sin function and cos of phi. So you can easily plot the radiation pattern and see what is the E plane and S plane radiation pattern of microstrip antenna. So the another parameter which is very much important for the aperture antenna is the gain. Gain is defined as 4 pi r square. This is the pointing vector divided by power input. And pointing vector can be found out from the electric field as E square by half eta naught. So you can find out the gain from the electric field also. In order to find the gain, we need to know how much is the input power Pi here. You know that gain, for the gain, the reference is the input power. For the directivity, reference is the total radiated power. We are interested in the gain of microstrip antenna. So we can find out approximately what is this power input to the microstrip antenna. Assume that the power is coming from a uniform transverse electromagnetic field, line of width Wm. WM is the width of the microstrip antenna, and not the microstrip antenna, of the microstrip field line. If you assume the width of the microstrip field line is WM, M for microstrip line, then power input can be found out as square root of WM EI square divided by 2 eta naught. Eta naught is the wave impedance for free space or intrinsic impedance of the free space. Epsilon r is the relative permittivity of the substrate we are using. WM is the width of the microstrip line. H is the height of the substrate. EI is the incident electric field. So from the EI you can find out what is PI. From the PI you can find out what is E naught. E naught was the amplitude of the uniform electric field which was existing in the aperture. You can find out that E naught square is EI square 1 minus gamma I square. Gamma I is the input reflection coefficient. So this is the incident electric field at the microstrip antenna. Some of them will be reflected, some of them will be transmitted. So if I want to find E naught square, then EI square 1 minus gamma I square. Gamma I is the input reflection coefficient of the microstrip antenna. So you can find out this input reflection coefficient of the microstrip antenna is, you find out what is the Z of the pads minus Z of the microstrip line, Z of the pads plus Z of the microstrip line. Z0 means is the characteristic impedance of the microstrip line, M for microstrip line. Z0 M is the characteristic impedance of the microstrip line. And we have also assumed the pads as a parallel plate transmission line. You can find out the characteristic impedance of a parallel plate transmission line. We have already done that at the beginning of this lecture. So ZOP was approximately eta naught by square root of epsilon r H by W. So you find out the characteristic impedance of the parallel plate microstrip line minus characteristic impedance of the microstrip line. Characteristic impedance of the microstrip line can be found out from this relation, eta naught by square root of epsilon r into tau 1 plus 1.3 tau plus 1.393 plus 0.667 log of natural log of tau plus 1.444, where tau is dependent on the thickness of the microstrip line and the width of the microstrip line, height of the microstrip line. Tau can be calculated as Wm by H. Wm is the width of the microstrip line, H is the substrate height, 0.398 T by H. T is the thickness of the microstrip line into 1 plus natural log of 2H by T. T is the thickness of the microstrip line. From here you can find out what is the characteristic impedance of the microstrip line. From here you can find out the characteristic impedance of the equivalent parallel plate transmission line of the microstrip antenna. From this relation you can find out the input reflection coefficient. So now we have most of the thing. We can find out what is the gain. So we are interested in finding the gain. So we need gamma I to find out what is E naught. E naught is the uniform aperture amplitude of the electric field in the slot 1 and slot 2. We also have this electric field here, and usually when we say gain of the antenna, this is the maximum gain. I want to find out what is the maximum value of this. So we have the electric field in the far field. Maximum value will be, and theta is equal to pi by 2. This is the maximum value for the electric field, 2j beta exponential minus j beta r divided by pi r E naught HW. When theta is equal to pi by 2, this term becomes 1. Theta is equal to pi by 2. This will become 0, so cos of 0 is 1, so this term becomes 1. So we have the E max also. We can find out gain now. Gain is this relation here. You have 2 pi r square E square E max square divided by eta naught pi. Pi is this. E max we have just found out. We plug in those values, then we can find out gain of the microstrip antenna. So 2 pi r square, this is the E max. E max expression is this, square of that divided by, this is a pi. And you also have eta naught. So eta naught is also there. This is expression for pi. This is eta naught. What you can do is you can cancel out many terms here. Eta naught can be cancelled out. You simplify all this term. Very simple. Finally, what you get is gain is 64 pi by square root of epsilon r wi by lambda I square w by wm 1 minus gamma I square. So this is the expression for maximum gain of microstrip antenna. So we would like to see what is the typical gain of a microstrip antenna. What is the typical gain of a dipole antenna, Hertz dipole? 1.5. No? So what is typical gain of a microstrip antenna? Let us try to see this by taking typical values of gamma I. Gamma I is usually less than or equal to 0.25. W is width of the microstrip antenna is always greater than or equal to 2 times the width of the microstrip line. W is usually taken as 0.25 lambda, that is lambda by 4. Ice is taken as 0.1 lambda. Ice is usually very small. Epsilon r, let's say we consider FR for substrate, that's a PCB substrate you use in the PCB fabrication, and it has a epsilon r of 4.4. You plug in these values and what you find out, gain, maximum gain of the microstrip antenna turns out to be 4.49. It's a decent gain, and if you consider this in dBi, it is 6.5 dBi. Usually microstrip antenna has around 6 to 9 dBi gain, and this is a typical value of a microstrip antenna gain. So we have discussed about finding the far field radiation pattern of a microstrip antenna, and the model we have considered is the aperture model of the microstrip antenna. There are many different models of the microstrip antenna. Some of them are transmission line model, another is called cavity model. Aperture model, because we have considered this microstrip antenna as a part of aperture antenna in this course. We have discussed many aperture antenna. This is the last antenna we will be discussing on the aperture antenna, and we have found out easily the radiation pattern of the microstrip antenna using the aperture model, and after that we find the gain of the microstrip antenna also, and it has been observed that gain of the typical gain of the microstrip antenna is around 6.5 dBi. That's all about discussion on the microstrip antenna. In the next slide, we will actually discuss some of the microstrip antenna and its variants, which has been originated from our research group. These are some of the design of microstrip antenna, which is an advanced version of microstrip antenna, which has been originated from our research group. We'll discuss 3 of them. The first one is dual band folded strip printed monopole antenna for RFID and wireless LAN application. So this is a dual band microstrip antenna or printed monopole antenna. See, basically for the microstrip antenna, the ground plane is printed with metals. Let's say you take out some portion of the ground plane, what you will observe is that the bandwidth of the microstrip antenna increase significantly. One of the major drawback of microstrip antenna is that it has a very low bandwidth, narrow bandwidth, usually around 5% up to 10%. But let's say if you remove ground plane, partially its ground plane, you remove some portion of the ground plane, you have to design it properly. You can refer to any of these papers I mentioned here. You can easily design it, remove some portion of the ground plane, and when you remove some portion of the ground plane, the bandwidth of such kind of antennas usually is very high. It can have more than 100% bandwidth also. Without the with the partially its ground plane, we can have bandwidth around 100%, even more than that. But let's say if we have a full ground plane without any etching, then usually that's a traditional or conventional microstrip antenna usually have a bandwidth less than 10%. So these 3 antennas we have considered here is called printed monopole antenna with the partially etched ground plane. Some portion of the ground plane has been removed to have higher bandwidth, and this is one of the very popular microstrip antenna, and people usually call this antennas as printed monopole antenna. We have done a lot of research on the printed monopole antenna. So these are some of the work with my PhD students. This is the work with my second PhD student. We have designed a dual band printed monopole antenna for RFID and wireless LAN application, and this remaining 2 works are with my 5th PhD student, and We have designed printed triangular monopole antenna for ultra wideband applications. So the antenna we have considered is rectangular microstrip antenna. As I already told you, the pads can be of different shapes. When we have a printed triangular monopole antenna with some very good design, we can have ultra wideband performance. So bandwidth is huge. It's no more a narrow band microstrip antenna. This printed monopole antenna is ultra wideband monopole antenna. Then we also design a printed monopole antenna with tapered fit line, fit region, and pads for super wideband applications. A huge bandwidth. Basically, in the initial research, we always try to extend the bandwidth of the microstrip antenna by applying many techniques. This is one of the outcome of that. We have a super wideband printed monopole antenna. We'll briefly look at the structure of these three antennas. This is the first antenna. Basically, in this first antenna, see, the ground plane is up to here. So this substrate is, see, substrate is from here to here. So this substrate is having a dimension of 50 by 35. 50 by 35. This dimension is 50 by 35. Substrate dimension is there. But the ground plane, look at the ground plane. We don't have a ground plane up to here. So we have removed this portion of the ground plane. This portion of the ground plane, and the ground plane is from 18 to 35. So we have removed this portion completely below the ground plane of this microstrip antenna. This is a fit line. This is the structure of the pads. We have folded the antenna, so that is a folded monopole antenna. Monopole antenna because we have removed this ground plane here. People usually call this kind of antenna as monopole antenna. This is no longer a microstrip antenna. This is a printed monopole antenna, which is the variant of microstrip antenna with a partially its ground plane. So we have a folded structure here. This is one resonator, resonator part 1. This is another resonator. We actually put a stub in the ground plane. This is the resonator part 2. So this resonator 1 and 2 will give me dual band performance, one for RFID application, one for wireless application. For the RFID application, center frequency is around 2.4 GHz and bandwidth is from 2.05 to 2.86 GHz. And for the wireless LAN application, center frequency is 5.81 GHz. Bandwidth is from 5.55 to 6.14 GHz. If you are interested in this antenna, you can refer to this source here. Second antenna, as I already told you, is a printed triangular monopole antenna. Look at this. This is a ground plane. So here substrate is having a dimension of W and L, but you see that this ground plane portion has been removed. So this is no longer a microstrip antenna. We call this as printed monopole antennas. And the structure of this pads here is triangular in shape. That's why we call it printed triangular monopole antenna. And you see that there is some change in this width of the microstrip line. See, this is a fit line. Fit line has a microstrip width of WP. We have an impedance matching here. See, basically we have used step impedance matching here. So that's why we have a huge bandwidth. This antenna works from 1.8 to 15 GHz. We have fabricated and tested all this antenna, and it is giving a measured bandwidth from 1.8 to 15 GHz. This is another printed monopole antenna we have designed in our lab. So this antenna, as I have already told you at the beginning, we want to have a higher bandwidth for the microstrip antenna, or let's say printed monopole antenna. So now this is the fit line here. Fit line is no longer rectangular. You have a taper here. Rectangular, then it should have same width everywhere. You have tapered it here. Then we call this region as fit region. No? This region is called fit region. We also use a taper here. Even the patch is also exponentially tapered. No? So we have actually dissected the antenna design into three parts. One is fit line, another is fit region, another is a patch. And what we have done is we have actually tried to optimize the try to minimize the reflection in every portion. So here we have used the best fit line with the maximum impedance matching, broadband impedance matching. Even the fit region also, we actually make it so that there is minimum reflection here. Even from the pads also minimum reflection. So we have used tapered in the fit line, tapered in the fit region, and pads also tapered. In that case, signal which comes from the source goes to these pads with minimum reflection, and it's getting radiated into the free space. And what we have observed is this antenna can have impedance bandwidth from 2.5 to 80 GHz. So this is a super wideband printed monopole antenna, and if you are interested, you can explore by following this link. That's all for this class, and this is the last lecture on this course. I hope you have enjoyed this class. Thanks a lot for your time and cooperation, and I hope that I will take one more class in your next semester. Thanks for your time.